Okay, I will talk about a little bit about singular points for second order ODE. So here is a form of the second order ODE. Y double prime equals to px y prime plus qxy. So the regular point, quite straightforward, is that at x equals to x naught, qx naught and px naught are finite. So, and we have a singularity if they're not finite. But it will classify the two different classes. Regular singular point, which px naught, x naught, x minus x naught, q x naught, x minus x naught squared is finite. At first glance, and then you have irregular singular point, same argument, but that become infinite. So at first glance, it's rather confusing, at least to me, why we classify into two different classes: a regular singular point and irregular singular point. So if you do a several exercise on problems, Frobenius method, which just make y equals to somewhat like a Fourier theory, but with an extra n to the rth power. And then you fit the y into here, and to solve for the coefficient, which I'm going to talk about later, for maybe for the next video. But for now, you can just think, well, if I do double prime, you get like in the order of y over 2x and plus. I'm just talking about the order, and I'm not talking about the actual solution or whatnot. The order will be the order of y prime is y over x. That will be q x y over x squared. So that is how we get the definition of why we use regular singular point and irregular singular point. Because if we have a regular singular point, the growth of the form of the series will be in the order of x to the n plus r. And if it's infinite at those point, of course, the x is at x approaching x naught. Then the growth rate is higher than the polynomial, which give us a bigger challenge, or we have to modify the Frobenius method to a different to a different one that we can actually solve irregular point, which I also think we're going to talk about in the Frobenius method. Yeah, that's a regular point and irregular point. Sorry, regular single point and regular single point and irregular single point. So what if we consider x naught as infinity? Well, it's really hard to calculate. I mean, it's not too hard. It's rather less intuitive to think about infinity than think about approaching zero. So at least the book that I read offers another method. Construct z equals to 1 over x. And just substitute this into the differential equation. You will end up have a second order differential equation like this: z to the fourth dy dx squared plus 2z cubed minus z squared p to the 1 over z, which is x, dy dz plus q 1 over zy. So the criteria for regular point and irregular point will become regular singular point. Give us z approaching 0 and give us x approaching 0, give us z approaching infinity. Singular point. The criteria will be 2z, sorry, z approaching 0 give us x approaching infinity. Sorry, infinity. I mean, positive or negative depends on which direction you're approaching to z, approaching to 0. P z minus 1. Those two are finite, given as z is approaching 0. So for irregular or singular point will be infinite. If you want to study the singularity, which type of singularity you have, singular point you have at x equal to infinity, that's the way you deal with that. Yeah, that concludes the singular point for now. Next, I will talk about Frobenius method on next video.